Thanks. Welcome everybody to the second instalment in this webinar series, Securing the Energy Grids of Tomorrow. So in this session, I want to talk a little bit about specific cybersecurity and general security aspects that affect smart grids. So to recap, our definition of the smart grid is we're moving from this centralized distribution of energy from generally rotating machines that have a significant amount of inertia. Grid management was done by monitoring the frequency of operation and looking at how heavily loaded that was. The smart grid moves away from that centralized model to a bidirectional flow with lots of generation sources, lots of energy sources, and adding storage as well, energy storage facilities. And also a much more dynamic grid where smart cells, smart brokers, smart agents are looking at buying and selling energy and connecting and disconnecting from the grid as they see either excess demand and not enough supply, or storing energy when there's excessive supply. So this general concept of a smart grid covers these things, but it needs time synchronization to operate. As before, as in the system before the smart grid, synchrophasers were making measurements of the electricity signal, measuring current and voltage with down to microsecond precision required. Sampled values are snapshots of the same thing. The IEC 61850 digital substation specification calls for PTP, the Precision Time Protocol, which means we usually have satellite-based sources of time for the reference clocks, and the PTP clients in the IEDs within the substation are all using the same notion of time. And also there's a level of synchronization required from the micro generation sources to make sure they're generating electricity in phase with the grid as a whole. So lots of requirements for synchronization and timing across that system. In terms of security, so our first look at security, typically the physical access controls are extensive. These are the electricity generation and distribution assets are physically very well protected. To get onto generation sites, there's normally some degree of segregation and fencing around the site. You need usually government issued ID, a photo ID, and then in some sites I've been to, there's biometric ID as well, where they scan your fingerprint on the way in, and then to access certain parts of the site you need the same biometric ID. So the physical controls on access, the physical security measures that are put in place are usually really extensive. And in terms of the Ethernet networks that might be using NTP or PTP, the process bus, the substation bus, they're typically private and isolated networks. So they're not connected to any other network where the public might be able to access them. And that's how they're supposed to be designed. So their security is by separation, private and isolated networks. But we have this condition where we rely on satellite timing receivers, GNSS timing receivers, to get time into these networks, to get an agreed global timescale UTC into these networks. In some cases, only for event reporting and fault logging. Then we end up with this sort of proliferation of antennas, and this is a photograph from a particular installation in the UK, where we see this proliferation of many different GNSS satellite time receivers, all serving the same purpose, to get time into this particular location. So the physical access controls may be extensive, but then we have this effectively open radio interface. So this is the GNSS signal, usually centered somewhere around the 1.5 gigahertz band, an open radio interface that attackers could attack, either jam or spoofing these signals. In terms of the operation of a GNSS timing receiver, the type that is used to get time into these networks, into our smart grid, for our smart grid to operate, they're typically the same design that's been around since the mid-90s, when the first commercial civilian applications for, at the time, they were GPS-only satellite timing receivers came along, where the position itself, the system, the satellite system is synchronized. It works out its position by ranging the receiver to the satellite. The whole system, all the satellites are all synchronized, and they're all synchronized and traceable back to a source of UTC. So by getting a position solution, we could also get very accurate time, but there is an inbuilt trust within these receivers going back to the mid-90s when they were first designed, where it wasn't conceivable that it would be likely that an attacker might spoof the signal. So the signal, the radio signal, in many of the timing receivers that are deployed today in existing infrastructure, there's an implicit trust built in that the radio signal is actually valid and it's telling us the right time. And that's the same for most timing receivers, even the multi-constellation, some multi-frequency receivers that use other constellations like Galileo, like Beidou and GLONASS. They do still have this implicit trust built in. So part of the problem for GPS is it's free and it works everywhere. That's one of the reasons why it's selected as a source of time. There's this proliferation from the mid-90s of GPS receivers. Back then, they were really only used for frequency sources with high accuracy. Other servers, NTP servers, began to use them for time and phase alignment. But there are billions of GNSS receivers now. They are embedded into our smartphones, so they have become a commoditized way of getting freely available, accurate time. Part of the problem with these satellite systems is their phenomenal uptime. So they're not only free and they work everywhere, but they work all the time. So there have been a few major issues. There have been a few. This one that's referenced on the slide, SVN23, is when an old satellite was being decommissioned. Some errors were made in that process, and the GPS constellation had half of the satellites with a certain timing and the other half of the satellites with a 13.5 microsecond offset to that time in them. And timing receivers were jumping between those two values. But that is one of the few, you could probably count on one hand, the major outages in GPS. Whilst it's been operational, it was declared fully operational in 1995, so it's been operational for a very long time. And it's typically seen as a fit and forget component or a module. In the power industry, lots of GPS timing receivers are modules from a certain manufacturer that are embedded in another manufacturer's timing module that's embedded by a system integrator into a rack or a suite of equipment. So it is typically this sometimes fit and forget module. It's just the module that gives you time, and it's there and it works all the time. And of course, GPS, as I mentioned, as a stratum 1 source for NTP, has us all addicted to stratum 1 time. So it's relatively trivial, even at home, to build yourself a stratum 1 NTP server from a Raspberry Pi and a small GNSS receiver. And NTP is everywhere. NTP is used as the de facto time synchronization protocol on packet networks. So part of the problem with GPS specifically and GNSS in general is it's free, it works everywhere all the time, and it's available over the internet as NTP Stratum 1 servers. In terms of smart grids and the power industry in particular, if we have two separate sites, here we have a site on the left and a site on the right, some high voltage distribution, some sort of current and voltage samples that are being taken by a measurement unit using a clock reference. Now, if they're both using GNSS, now I appreciate that some of these systems do have their own time scales. They do have their own mechanisms to make sure that each end is using the same time base. It doesn't necessarily have to be UTC traceable. As long as both ends is using the same clock to make a measurement, then they can usually get accurate. But as we move to smart grids, I think there's more opportunity for this sort of deployment to occur. where we're adding more and more smart monitoring. We're adding more and more entities that measure and make decisions based on those measurements into our smart grid by the very definition of the way the smart grid operates. So if somebody could corrupt the time at either end of this link, if somebody could convince one measurement unit that while it was making very high voltage samples, the other end was at the same time making low voltage, sampling the voltage and reading the low voltage, the system might deduce that there is a short, some sort of fault along this high voltage transmission line that means we're losing voltage somewhere, and shut that down. So it's a very real, threat, a real danger to these power distribution systems that they could be susceptible to time spoofing. So time as an attack vector. So if a bad actor wants to cause some damage to the smart grid, wants to cause some either just nuisance faults, just making intermittent faults appear so that they cause a nuisance for the distribution operator who has to send people out to site to try and investigate these problems, or if they want to cause something a little bit more sinister, like shut down local or maybe wider areas in terms of power, they could turn up on the left-hand side. At the bottom of the slide is our GPS, our GNSS spoofer. We've got some spoof signal. Our timing receiver is trusting the signal implicitly. We can maybe jam the receiver so it goes into signal acquisition mode. We can then turn on our spoofer at a higher power level than the signal that's received from the sky. And hopefully that timing receiver then locks to our spoofed signal. And we can do anything with the time then. We can either spoof it days, months, years into the future to try and cause problems, or we could perhaps be more subtle and try and spoof small time errors to try and provoke faults or shutdowns within the system. So it's just a very basic example. And as I said, I appreciate that this isn't by means every single distribution system operates this way. As I say, they do sometimes have mechanisms to ensure that both ends are using the same time base, but it's the opportunity, I think, that's presented by the smart grid with these smart decision-making autonomous systems that are all trying to use the same time reference. If the time reference isn't the same at a particular location, then we could hit problems. So any timing receiver that we have to appreciate that both jamming and spoofing could occur. They're now civilian activities. The GPS satellite system was designed as a military system. So when it was designed, they were particularly designing the system thinking that it might be other military entities or other nation states that had the capability to spoof the signal. But now, as we'll see, it's relatively easy to do that for civilians. So obviously, any local receiver, we need to protect against jamming, which is like a denial of service issue, or spoofing. So we need to either engineer our system to be able to hold over with accurate time if the signal goes away, or to be able to detect when we think someone is giving us a simulated signal that isn't the same as the signal from the sky. And obviously any solution must be engineered to survive intermittent and prolonged outages. So jamming is a civilian activity. There are ads on social media for so-called privacy jammers where people are worried about being tracked. You can buy these sort of cigarette lighter jammers, a couple of tens of milliwatts of power. The jammer is basically just a noise source that is higher power than the signal as it's received on the surface of the Earth. So it just creates noise. So the timing receiver can't hear the satellite signal, and causing the timing receiver to go into holdover. But spoofing now, as I mentioned, it is a civilian activity. It's almost trivial with commercial off-the-shelf computing hardware, commercial off-the-shelf software-defined radios, and some open source software to download, compile the software, and build yourself a fairly simple GPS signal simulator. The photograph at the bottom right shows a simulator that we built within Kronos as a proof of concept a couple of years ago with a Raspberry Pi and a Lime SDR software-defined radio. And the ethical hacker conferences, and I'm sure the unethical hackers too, have been talking about spoofing, generating GPS signals for many years. But it's really the awareness of location tracking and location services in smartphones and things that's really brought this to the forefront of public and civilian knowledge. So it's almost trivial now to be able to produce a spoofed GPS signal. But people always ask, just how much of a problem is it? How common is it? So if we want to find out anything, we turn to our favorite search engine. And if you look for spoofing reports on GPS, you'll find there are many, many reports, particularly all to do with location spoofing. So there's all sorts of issues with marine navigation around certain ports in Asia, certain heads of state that the thinking is that their secret service spoofed the location around the head of state to protect him from any drones or anything that might be trying to use these navigation services to attack him. So position spoofing is very common. In terms of time spoofing, there are several anecdotal issues when that's happened accidentally with GPS simulator manufacturers at conferences that haven't terminated some of their cables properly. So some simulated GPS signal has escaped and caused problems on people's smartphones. And also some anecdotal evidence of time spoofing actually happening to critical infrastructure. But obviously these are things that the operators of the critical infrastructure themselves don't want in the public domain. So what can we do about it? Well, we know the signal's vulnerable. We know we have this open radio interface to the sky. We have our Raspberry Pi based spoofer on the right-hand side. So we have our installed base of our timing receivers on the bottom of the slide. And we have our antenna that we trust the radio signal. So what can we do about that? Well, different things we can do. One of the new product categories that's been around for a couple of years now is the so-called GNSS Firewall. This is a signal analysis device, and also it contains within it a simulation, a simulator that can simulate the satellite signal. So in the middle, we have the antenna looking at the sky signal. The signal analysis portion of the device looks much deeper into the signal than the legacy timing receivers that are deployed in existing installations. It can look for things like changes in RF power level. So if we come along with our signal spoofer and we have a much higher power, that can be detected. It also obviously looks for position and time anomalies. So if our spoofer is telling us that there's a big jump in position suddenly or a big change in time, then the system can detect that. But it also looks at the signal integrity itself. So the satellites broadcast the so-called navigation message, which contains data fields about the health of the system, about all sorts of things. So the GNSS Firewall's job is to look at that data and to try and work out if it thinks it's a signal from the live sky or if it's a simulated signal. One of the problems with the Raspberry Pi spoofer and the open source code is that lots of that data is just left at default values. So it's relatively easy to spot in that case that it's a simulated signal. So what can the GNSS Firewall do? Well, it can decide to pass the sky signal through. So on the right-hand side of our slide, we have this so-called validated output, which if the sky signal is okay, then it passes that through to timing receivers, and we could have a splitter on that output. So we could then pass that validated signal to all of our timing receivers in a substation or in a particular installation. If it decides that the sky signal is being interfered with, then it can turn that validated output off. And if we have holdover in our time servers, then we can just let our time servers go into holdover. The other half, the left-hand side output of this GNSS Firewall is interesting because that is a simulated GPS signal. So it contains in itself a signal spoofer, if you like. So it's a GPS signal simulator that can generate a signal, a GPS-like signal based on its own time base, which could either be an optional internal rubidium atomic clock or an external cesium. So if we see GPS spoofing, we could then let all our all our installed time base of receivers follow our simulated GPS output and keep going. And that's obviously a benefit if our receivers don't have enough holdover to be able to serve their applications for long periods of time. We can interpose this firewall in the between the antenna and the receivers to give us extra performance and let us know through integration into management systems when these jamming and spoofing attacks are happening. Another thing we can do is we can put some of that functionality into the GNSS receivers themselves. Obviously, all that intelligence, the signal analysis, looking at RF power levels, position and time anomalies, we can add that into the newer generation of GNSS timing modules and receivers. But obviously, they're only going to slowly, over years, make their way into deployment. So we still have to somehow deal with this installed base of receivers that just implicitly trust the radio signal. Obviously, we can integrate our GNSS time sources with other sources of time, maybe from the network, from packet timing signals like NTP and PTP, other satellite receivers, the Iridium-based constellation, the low Earth orbit satellites, the Satales constellation, or other low-frequency time signal sources can be integrated into an overall timing system that we could spot then if our time from GNSS was being spoofed. And there's also interference detection antennas that are basically an array of antennas, and with extra software we can then steer a null in the reception pattern towards the signals that we decide we don't like the look of, whether they're jamming signals or spoofing signals. So there are other mitigations apart from the GNSS firewall, but the GNSS firewall has the potential to protect the existing so-called legacy timing receivers. So in terms of satellite timing receivers, we've covered the threats to those, but what about NTP? NTP has long been a popular attack vector for hackers, for bad actors who want to try and cause problems in networks. Just doing a quick search on the National Vulnerability Database that NIST operate in the United States, doing a quick search for NTP, matching the case. There's over 500 vulnerabilities listed. So typically they are being able to intercept communications between NTP client and server, hijack the time and shift the time, or being able to send fragmented packets to cause issues with NTP, or using this technique called amplification to create distributed denial of service attacks. So effectively an attacker would spoof the source address of NTP packets and be able to sort of flood the NTP server with lots of requests appearing to come from different sources. So how can we deal with those? Well, the current generation of NTP servers have features like NTP in hardware. So they're called an NTP reflector, where on the right-hand side at the top of the slide, we have the green square that is a hardware implementation of NTP. So it's typically FPGA based. We can do hardware packet filtering to make sure that only NTP packets get to the NTP reflector. The NTP algorithm can be run and satisfied in the hardware entity, so it doesn't go anywhere near the CPU. Typically, NTP is a software-only software timestamp protocol, and that's how these denial of service attacks come about. When we flood the NTP server with either malformed packets or tampered with packets, we can overload the CPU and cause the NTP server to be unavailable to serve as actual time. But this technique of using a so-called NTP reflector in hardware means that most of the non-NTP packet can be dropped, easily filtered in hardware, and the performance of the NTP itself can be improved by having this hardware entity with hardware timestamping. So in terms of this NTP reflector, it gives us security, not only security, but performance enhancements as well. Very accurate timestamps, and can accommodate, in this particular example, over 350,000 NTP requests per second. but it's that idea of using a hardware entity, a hardware realization of NTP to increase performance. So NTP, as we said, has typically been an easy target for for some bad actors to cause denial of service and interfering with the time and time shifting our time servers. So in summary, to summarize what I wanted to speak about today in terms of securing the energy grids of tomorrow, fundamentally we know that the smart grid, as it's known, requires time synchronization. Cybersecurity practice should not just, traditionally it's been concerned with Ethernet networks and network access and the physical protections and physical controls around getting access to network elements. But we mustn't forget the radio interface. We mustn't forget all those GNSS RF antennas that are just looking to the sky, looking for a signal that they implicitly trust. So I talked about some ways that we can protect those GNSS signals. Also, we can augment time servers with other sources of time, like low Earth orbit satellites, or maybe network-based backups, or maybe some low-frequency time services as well, to augment the time service as a whole, to protect the smart grid, so to provide resilient and robust time delivery. We should assist the functioning of the smart grid itself. And not to forget, NTP servers themselves have for many years been targets for attacks, and obviously we've looked at a couple of ways of hardening those and increasing performance at the same time. So thank you very much for listening. That's the end of this session. We have another session coming up on the 7th of December at the same time. That concludes everything I wanted to say for now. Are there any questions?
Thank you, Chris. Jeff has come in and asked, he's heard that GPS and Galileo are adding authentication signals to their broadcast. Do you think these will completely remove the threat of spoofing?
Yeah, that's a good question. So one thing I didn't mention was to try and put smart features into the receivers. Both GPS and Galileo are both testing authentication signals. So GPS has a signal called Chimera, which I believe they are starting live trials, trials from the live constellation next year. Galileo has recently announced this OS NMA service, which is an authenticated service. And so they will, in fact, then enable a receiver to be able to listen to the signal and work out if it thinks it's an authentic or a simulated signal. There's a couple of issues with that, in that it's only going to be in new receivers or receivers that are able to have firmware upgrade, and the firmware is able to support that. So it's still not going to solve the problem of the huge installed base of receivers that we see, not just in the energy industry, but in all the other industries, the telecom and financial industries, data centers, where we have lots of timing receivers. But also, in terms of testing and proving as well, we need to be able to use GNSS signal simulators do have valid uses in labs and in test scenarios. So we need to somehow have a way of allowing the receiver to be able to receive a non-authentic signal and work. So maybe there'll be some configuration in these new receivers. And if there's a configuration to turn it off, to turn the authentication off, then again, it gives the attacker a chance to be able to get into the receiver somehow, maybe through a network-based attack, and disable the authentication. So it's a good question, and the satellite constellations themselves are taking stock of some of these issues and are trying to put in place systems to reduce the occurrence. So I don't think we'll ever get rid of completely the threat of spoofing, but I think these GPS and Galileo systems that have been announced will greatly reduce the opportunity for spoofing, if that makes sense. So